All right, this week we're going to learn about conservation of momentum. Our equation that we're going to work with all week is this one. m1v1 plus m2v2 is going to be equal to m1v1 plus m2v2. This is two objects before they collide with each other, and then this is the two objects after they collide with each other. So this is the base equation we're starting with. Some vocab for the week is perfectly inelastic, inelastic, inelastic. Perfectly inelastic is when two objects are not together before they collide, but then they stay together after they collide. Your kinetic energy is not conserved in this situation. Inelastic collisions could be set up several different ways, but the energy in an inelastic collision is not conserved. For elastic collisions, we can say that our kinetic energy is conserved, and these are the three things to consider, or names that we can call our collisions. But we're going to start with this equation each time. I'm going to just show you a few examples. I'll probably make 2 videos because I want to show you, I guess, more than a few examples. So the big thing here is to be able to pull out our variables. Number one, let's write our equation first. m1v1 plus m2v2 is going to be equal to m1v1 plus m2v2. This is before the collision. You could put an I down here if you want, and then this is going to be after. You can put an F for final down here if you want. It gets pretty lots of letters, so I tend to not include the initial and final just because I know before my equal sign is going to be before the collision, and after my equal sign is going to be after the collision. All right, so during a homemade cannon demonstration, a mass of 1.27, because it came first in my word problem, I'm going to put it first in my list for no other reason than that, is loaded with a tennis ball. So this will be my mass 2, and it's in grams, and we need it in kilograms. All right, are placed on the floor. So we can say that they are initially at rest. The velocities of both the cannon and the tennis ball are going to be 0 meters per second. This is our initial velocities. And the explosion stuns the crowd and propels the ball forward. A photo determines that the cannon recoiled backwards with a speed of 7.8 meters per second. What is the velocity of the tennis ball? So my V final for the cannon, which we identified as M1, so I could say V1 final is going to be 7.8 meters per second. It says it went backwards, so I'm going to identify it as negative, and I'll identify the velocity of the tennis ball as positive. It actually doesn't matter which one you identify as negative or positive. If you've got two objects and they're starting from rest, one of them will be moving forward and one of them will be moving backwards after they explode from one another. So one way you can modify this equation, because we just have the one initial velocity, they're moving or are together before the collision. So I would set up my before part of my equation this way, and this tells me that they are together before the collision, and then they're definitely after the collision, they're definitely away from each other, moving away from each other. So I'm going to keep them separate in my equation. So this actually cancels out because my velocity is 0. So anything times 0 gives me 0. My M1 is 1.27, and my velocity after the collision is going to be negative 7.8, plus my mass of the tennis ball times the velocity that I'm looking for. when I rearrange my equation, all right, this gives me, I guess I'll show it, negative 9.906 plus 0.054b. I'm going to add the 9.906 to both sides. And then I'm going to divide both sides by 0.054. Okay, this gives me a velocity of the tennis ball of 183 meters per second. And this is going to be in the forward direction. So if I did not identify this as negative, right, this would be negative because of how my equation worked out. It's okay if one is negative, if this one's negative and this one is positive, just as long as you identify one is negative and one is positive, or are comfortable with the idea that one will be negative and one will be positive. This is one. All right, let's try another one. All right, we got Hayden with a mass of 24.3, so he will be M1. Going on a skateboard with an initial velocity of 8.6. We can say he's moving in the forward direction. He travels underneath the low-hanging branch of a tree where Matthew is sitting. Hayden grabs a 4.5 kilogram bag of soccer balls. So this is going to be my M2. Kilograms. And we could say that the initial velocity of the soccer balls is going to be 0. It's at rest before Hayden grabs it. Determine the speed of Hayden immediately after he grabs the soccer balls. So we want our final velocity of our whole system. All right, so our base equation looks like this. And B, 1, 1, 2, 2, 1, 1, 2, 2. But when I read my word problem, I know that Hayden is moving with some forward velocity, but the ball is at rest, so I can cancel this off. And I can set it equal to when Hayden is on his skateboard and after he grabs the balls, they're moving together with one velocity. The balls and Hayden are traveling at whatever the new speed is going to be. So my equation, my base equation, can be pared down to this equation here. This is going to be the final velocity of both objects. This is going to be our initial velocity of Hayden. So when I plug my variables in, this one was easy enough to rearrange because there's not so many variables, but in general, I recommend that students just plug it into the equation. I know this is not my standard, but I do think that it is easier when looking at this equation, just because you've got a lot of M's and V's that are hard to keep track of sometimes. So 24.3 times 8.6. This will be the initial momentum of the boy. And we're going to divide that by the mass of both him and the soccer balls post-collision. So because my mass essentially is going up, I expect that my velocity is going to be going down. Right? We're moving with a greater mass here, so my velocity should be something less than the 8.6. Okay. All right, and it is 7.3. We'll round. Right, less than the original 8.6. That makes sense. All right, so we're always going to start with this equation, but we can make it smaller based on if they're moving together before or together after. And you, reading the word problem, can decide if it's together before or together after. This is essentially what you need to ask yourself each time. Are these things together before or are these things together after? And how can I make my equation to match that?